Do this with me, right now. Go to your kitchen and touch a metal spoon sitting on the counter. Hold your fingers there for 2 seconds. Now touch a wooden cutting board right beside it. The spoon feels cold, the wood feels warm. But here's the problem. They have been sitting in the same room, breathing the same air, for hours. If I put a thermometer on both, they read the same temperature. Exactly the same. So why does your hand report to completely different realities? Because your hand is not a thermometer. Your hand is something far more primitive and far more dangerous. It is a heat flow detector. It doesn't feel temperature the way you think. It feels energy leaving you or entering you, and it makes a judgment fast. Cold, warm, safe, danger. And that tiny kitchen trick exposes one of the deepest misconceptions people carry about physics. And it actually is. By the end of this, you won't just know the answer. You'll feel it differently forever. Start with a simple fact everyone has experienced. You set a hot coffee cup on the table, and an hour later the coffee is cold. Where did the heat go? People say it dissipated into the air. The table, the room, fine. But what is that heat? What actually moved? For a long time, humans believed heat was a substance, an invisible fluid that lived inside objects. They called it caloric. Hot things had a lot of it. Cold things had less. Put them together and caloric would flow from hot to cold like water flowing downhill until everything balanced. It was elegant. It explained why hot objects cool. It explained mixing hot and cold water. It explained expansion when heated. It sounded complete. But then reality attacked the story. A man named Count Rumford was supervising the boring of cannons. In Bavaria, metal being cut got extremely hot enough to boil water. Under the caloric idea, you'd say the tool is squeezing caloric out of the metal. But Rumford noticed something that should have been impossible. You could keep the boring tool moving, and the heat kept coming out, again and again and again. If heat were a stored fluid, the metal should run out. But it didn't. It produced heat as long as motion continued. That observation is like a hammer hitting the caloric theory in the face. Rumford's conclusion was radical for the time. Heat is not a substance. Heat is motion. Heat is microscopic motion. Heat is jiggling. Now let's build the real picture. Everything is made of atoms and molecules, and they are never still, in solids. Atoms vibrate in place like masses on springs. In liquids, molecules slide, rotate, collide, and rearrange. In gases, molecules fly freely and crash into each other and the walls. Temperature is not how hot something feels. Temperature is a measurement of the average microscopic kinetic energy, how intense the random jiggling is. Faster jiggling means higher temperature. Slower jiggling means lower temperature. And here's the point that fixes everything. Objects do not contain heat. They contain internal energy. The microscopic jiggling energy stored in the motion of their particles. Heat is not a thing. Inside an object, heat is the name we give to energy while it is being transferred from one object to another because of a temperature difference. Heat is energy in transit. Like money in your bank account versus money being transferred. The balance is internal. Energy, the transfer is heat. This sounds like a language game until you realize it solves the spoon puzzle instantly. Your hand is warm. The spoon is cooler when they touch. Energy flows from your hand into the spoon. Your nerves detect that flow, not the spoon's temperature. So the real question becomes, why does energy leave your hand faster into metal than into wood? That's where the physics gets beautiful. Metal has high thermal conductivity, energy moves through it extremely quickly, not just because atoms vibrate, but because metals have free electrons, mobile charge carriers that can zip through the material and carry energy away fast. The moment your skin warms the tiny contact spot, metal rapidly transports that energy deeper into the spoon, so the surface stays relatively cool, constantly pulling more energy out of your hand. Your hand experiences a rapid drop in skin temperature at the contact point. Your brain screams, cold. Wood is the opposite. Wood is a poor conductor. Its structure includes complex cellulose chains and lots of trapped air pockets. Energy cannot rush away. When you touch wood, the contact surface warms up quickly and then the heat flow slows because wood can't transport the energy away from the surface sufficiently. Your skin doesn't cool as fast. Your brain says, warm, same room, same temperature, completely different heat flow rate. And that is why coldness is not something you touch. It's something you lose. Now let's make it even sharper. There's another property that explains feel even better than conductivity alone. It's called thermal effusivity. You don't need the math on screen, but you need the idea. Conductivity tells you how fast energy moves inside a material. Effusivity tells you how aggressively a material can exchange heat with your skin when you touch it. It's the reason tile feels colder than carpet even if they're the same temperature. Materials like metals and stone have high effusivity. They can pull heat from you quickly. Materials like wood, plastic, foam have low effusivity. They can't. So your skin's first impression is mostly effusivity. That's what your nervous system is responding to in the first second. Now, here is a thought experiment that breaks people's intuition. Take 2 blocks. One is aluminum and one plastic. Leave both in a freezer until they reach the same cold temperature. Then take them out and place an ice cube on each block. Which ice cube melts faster? Most people say same temperature. Same melting. Wrong. The ice cube on aluminum melts faster. Why? Because the room begins warming the surface of both blocks. Aluminum conducts and delivers that incoming energy to the ice efficiently. So the ice receives energy faster and melts faster. Plastic cannot deliver energy to the ice as quickly. Same temperature does not mean same behavior in heat transfer. Temperature is the state. Heat transfer is the process, and your body lives in processes, not labels. Now let's kill that dangerous everyday phrase. Close the door. You're letting the cold in. Cold is not a thing. Cold doesn't flow. There is no cold fluid sneaking under your door. What's happening is heat flows out from the warmer inside to the colder outside. The only thing that moves is energy. Cold is a description of lower temperature, not a substance. This matters because if you think cold is a thing, you will misunderstand insulation, refrigerators, and even why certain materials feel the way they do. So what does insulation really do? A blanket doesn't produce heat. A blanket at room temperature is not warm. You feel warm under a blanket because your body is a heat engine producing energy non-stop roughly. Like a light bulb's power. Without insulation, you lose energy quickly to the air, especially by convection as warm air near your skin rises and is replaced by colder air. A blanket traps a layer of air. And air is a terrible conductor. So the blanket slows heat loss. Your body warms the trapped air. The heat flow rate out of your skin drops. Your brain interprets that as warmth. In winter, blanket slows heat leaving you. In a hot desert, clothing can slow heat entering you. Insulation doesn't pick a side. It fights heat flow in any direction. Now, we need the 3 heat transfer mechanisms because they appear everywhere in real life. Conduction. Direct energy transfer by collisions and vibrations, strongest in solids, especially metals. Convection, heat carried by moving fluids, air, and water. Hot air rises because it becomes less dense. That circulation transports thermal energy. Radiation, energy transfer by electromagnetic waves. No contact required, no air required. That's how the sun heats Earth through the vacuum of space. You feel a fire across the room mostly by infrared radiation. You are literally absorbing invisible light and turning it into microscopic jiggling in your skin. Now, the final nail in the caloric coffin came from James Joule. He built an experiment with falling weights turning paddles inside water. The weights lost gravitational potential energy. The paddles stirred the water, and the water warmed up. No flame, no hot object added, just mechanical work turning into thermal motion. Joule measured it carefully and found a precise relationship between mechanical work and temperature rise. Energy is conserved, just changing forms. This is why we measure heat in joules today. Heat isn't a mysterious fluid, it's energy transfer. Now let's come back to your hand again, because this is where the viewer's mind flips. Your skin has thermoreceptors, but they are not objective instruments. They're survival sensors. They mostly detect changes. Am I cooling quickly? Am I heating quickly? And that creates illusions. Try this. Get 3 bowls, one with cold water, one with warm water, one with room temperature water. Put one hand in cold for a minute and the other hand in warm for a minute. Then put both hands into the room temperature bowl. One hand will swear the water is warm. The other will swear it's cold. Same water, to different perceptions. That proves it. Your nervous system is measuring heat flow relative to your current state, not. Reading absolute temperature like a thermometer, the spoon and cutting board are the same trick, just disguised. Now let's push the spoon experiment deeper. If you keep your hand on the metal long enough, something interesting happens. It stops feeling so cold, not because the metal changed nature, but because the temperature difference shrinks at the contact point as your hand and the spoon surface come closer to a common temperature. The heat flow rate drops, and the sensation fades. That's why the first second is the strongest. Perception follows flow rate. Now, I want to answer the question people ask next. If metal pulls heat from my hand, why does it also burn me faster when it's hot? Same reason. High effusivity works both ways. If the metal is hotter than your skin, it can deliver energy into you very fast, raising your skin temperature quickly, causing burns. Wood, being a poor conductor, often burns you slower at the same high temperature, though it can still burn. The direction of heat flow flips depending on which is hotter, but the speed advantage of metal remains. Metals exchange energy aggressively. Wood exchanges energy reluctantly. Now let's connect this to real homes in London, Europe, and the US in a London winter. A house with poor insulation loses heat rapidly. Warm indoor air transfers energy to the walls, windows, and outside air. The heater isn't making the house warm forever. It's constantly replacing energy that is leaking out. Better insulation means slow leakage. Less heating required. In many parts of Europe, thick insulation and efficient windows reduce the heat flow rate, keeping indoor temperatures stable with less energy. In many US homes, central systems manage heat mostly through convection, moving air around, while insulation slows the overall heat loss through conduction. This is why energy bills are basically a measurement of how fast your home is bleeding energy to the environment. Now let's go back to the beginning and lock it in. The spoon feels cold and the wood feels warm, though they are the same temperature. Because temperature is not what your skin reports. Your skin reports heat transfer rate. Metal conducts and exchanges energy fast, so it drains heat from your hand quickly. And your brain labels that as cold. Wood exchanges energy slowly, so your hand stays warmer, and your brain labels that as warm. Your hand isn't lying. It's just not measuring what you think it's measuring. And once you understand that, you understand something bigger. Heat is not a substance, not a fluid, not a thing trapped inside objects. Heat is energy moving because of a temperature difference. Heat is transfer. Internal energy is what objects have. Heat is what happens between them. That is the real physics, and once you see it, you will start noticing it everywhere, from coffee cooling, to blankets working, to why tile feels freezing, to why metal burns fast, to why the sun can warm your skin across empty space. That kitchen spoon wasn't a small mystery. It was a doorway.